So in this video, we'll be looking at Kepler's laws. The first two laws deal with conceptual ideas. So Kepler's first law is a very simple idea. It just says that an object orbiting the sun, a planet orbiting the sun, moves in an elliptical orbit around the sun. And the sun is at one focus of the ellipse. There's nothing at the other focus. Um, when we look at these problems, we're going to be treating the orbits as circular, which is a fairly good approximation. They are elliptical, but the eccentricity of the orbits is very close to zero, which means that they're almost perfectly circular. And for simplicity, we will be treating them as circular. Kepler's first law can also be applied to any object orbiting another much more massive object. The object orbiting the more massive object will follow an elliptical orbit, and the very massive object will be located at one focus of the ellipse. This doesn't work for things where the masses are close to each other, because technically they orbit the center of mass of the two objects. But when one object is much more massive than the other object, the center of mass is approximately at the center of the massive object. Again, just a reminder on eccentricity for ellipses. The eccentricity describes how elliptical it is, how stretched out the ellipse is. An ellipse that's perfectly circular has an eccentricity of 0. An elongated ellipse has an eccentricity close to 1. So the more stretched out the ellipse is, the closer that eccentricity is to 1. Most of the planetary orbits are nearly circular. They have eccentricities that are below 0.01 or below 0.02, which is almost 0, which is why it is okay to treat them as being circular in the things that we're going to be looking at. Kepler's second law is also a conceptual idea. His second law says that a line joining a planet and the sun, or a satellite and the object it's orbiting, it sweeps out equal areas in equal time intervals. So that means that if I look at this line from the sun to the planet, and I look at the line from the sun to the planet at some later time, this area that's swept out in, for example, 6 months. If I would look at a line from the sun to the planet here when it's at position A, there, and then if it's in position B again 6 months later, if I would look at this area that's swept out, those two areas would be equal to each other. This comes about for a couple of reasons. One of them has to do with conservation of angular momentum, which is something that we will look at later. But this also comes from the idea of energy. The closer the planet is to the sun, the lower its potential energy is, which means that the greater its kinetic energy needs to be. We'll talk about conservation of energy, and we'll see that the potential energy plus the kinetic energy for something in orbit must equal a constant value. So smaller potential energy means a greater kinetic energy, which means a greater speed. And so what we are really interested in is the fact that when the object is closer to the sun, it is moving faster. And so the closest approach to the sun is referred to as perihelion. That's where the object is going to be moving the fastest. And then aphelion, that's the farthest point from the sun. That will be where the object is moving the slowest. Again, the majority of things that you need to know with Kepler's second law is just the closer the orbiting object is to the orbited object. So the closer the planet is to the sun, the closer a comet is to the sun, the faster it is moving. Kepler's third law is the one that is used a lot more in terms of calculations. Kepler's third law relates the period of the orbit to the length of the semi-major axis cubed. And for circular orbits, this semi-major axis is just the radius of the orbit. So this says that the period of the planet squared will equal the radius of the orbit cubed. Again, technically it's the semi-major axis cubed, but for circular orbits, which is the cases we'll be focusing on, that will be the radius of the orbit cubed. This is something that in the next slide I'm going to prove based on Newton's law of gravitation. So Kepler didn't understand why this was true. He just knew that it worked based on the data. He had the data that showed the orbital radius of the different planets, and he looked at the periods of their orbits, and he saw that this relationship was true. It was an empirical relationship. When Newton came up with the law of gravitation, this was able to be used to prove why Kepler's third law should work. So to do this, we're going to have the sun, and the sun's going to have a mass, m sun, and then we're going to have a planet in orbit around the sun. The mass of the planet will be m planet. The radius of the orbit of the planet we're just going to call r. And so the force that's acting on the planet will be the gravitational pull of the sun. That's the only force acting on it, so the net force acting on the planet will be the gravitational pull, which is given by the gravitational constant g times the mass of the sun times the mass of the planet divided by r squared. Also from Newton's second law, we know that the net force equals mass times acceleration. So that's going to be the mass of the planet times the acceleration, but this is moving in a circle, so we're going to look at the centripetal acceleration, which is the speed squared divided by the radius. And if I combine those two things together, I get that the mass of the planet times the speed squared over the radius is going to equal g times the mass of the sun times the mass of the planet divided by the radius of the orbit squared. And so from this, we see that the mass of the planet divides out. And I can multiply both sides by r, so one of the r's goes away. And so I get that v squared equals g times the mass of the sun divided by the radius of the orbit. Or this orbital velocity will be the square root of g times the mass of the sun over r. This is not Kepler's third law, but this is one of the important equations that we need. It relates the orbital velocity of a satellite to the radius of the orbit. So in quite a few problems, you'll be told, a satellite is orbiting the Earth. So the m that you would use in that equation would be the mass of the Earth. Again, this mass right here is the mass of the orbited object. So the orbital speed would be the square root of g times the mass of the orbited object divided by the radius of the orbit. And so if you know v and r, you can find the mass. If you know v and the mass, you can find r. If you know the mass and r, you can find v. But if we want Kepler's third law, if I go back to this other version of the equation before I took the square root. I can also use the fact that the speed of the object is the circumference, 2 pi r, divided by the period, or that v squared is 2 pi r, that whole quantity squared, so that's 4 pi squared r squared over the period squared. And I can take this and substitute it in for v squared. So I have 4 pi squared r squared over the period squared equals g times the mass of the sun divided by r. And if you remember Kepler's third law, this was relating the period to the radius. So we need to get the period squared on one side of the equal sign. So I can multiply both sides by the period squared. And I can multiply both sides by r. And then if I divide both sides by g times the mass of the sun, I get this 4 pi squared over g times the mass of the sun the 4 and the pi and the g and the mass, those are all constants. So this says that the period squared equals some constant number times the radius cubed. And so if we double the radius, then r cubed becomes 8 times bigger. So the period would be the square root of 8 times bigger. Again, we have this relationship, changing the radius will change the period, and it's not a simple, you double the radius, you double the period. You have to think about it a little bit more closely. So tripling the radius, you would have to do 3 cubed, but then take the square root of that. That would give you how many times bigger the period would get. These types of problems can be used when we do orbital motion. So if we have a 100 kilogram satellite in a low Earth circular orbit with a radius of 1.2 times 10 to the 7th meters, and we want to place an identical satellite in a circular orbit with twice the orbital period, the first thing that we might be asked to do is to find the speed of the first satellite. So in some of these things were things that were derived on the previous slide, but with this orbit, we have that the net force acting on the satellite is going to be the gravitational force. And so the mass of the satellite times the acceleration, v squared over r, is going to equal g times the mass of the Earth times the mass of the satellite divided by r squared. The mass of the satellite divides out. We multiply both sides by r. And so we get that the orbital speed is the square root of g times the mass of the orbited object, in this case that's the mass of the Earth, divided by r, which is the radius of the orbit. So in this case, this would be the square root of g, which is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And then we have the mass of the Earth, 5.98 times 10 to the 24th kilograms, divided by the radius of the orbit, which is 1.2 times 10 to the 7th meters. And if you plug those numbers in, you get that the speed of the first satellite is 5,765.3 meters per second. So this is a very common problem to be asked to find the speed of a satellite given the radius of its orbit. If we want to find the radius of the second satellite, all we know is that the second satellite has twice the orbital period of the first satellite. So the first thing that we need to do is find the period of the first satellite. So that period of the first satellite is going to be 2 pi r over the speed. Again, the speed is 2 pi r over the period, so the period is 2 pi r over the speed, which is 2 pi times the radius, 1.2 times 10 to the 7th meters, divided by the speed that we just calculated, 5,765.3 meters per second, which is 13,077.9 seconds. The period of the second satellite, we're told, is 2 times the period of the first satellite. So that's going to be 26,155.8 seconds. Again, by looking at the equation we had previously, this equation for orbital speed, we can look at that equation again. Again, if we didn't remember it, you could quickly come up with that. So the speed squared would be g times the mass of the Earth divided by the radius of the orbit. But we know that the speed was 2 pi r over the period. And so taking this and substituting it in, again, we're coming up with Kepler's third law here again. So we get that 4 pi squared r squared over the period squared equals g times the mass of the Earth divided by r. Or we get that the period squared is going to be 4 pi squared over g times the mass of the Earth times r cubed. Again, this is Kepler's third law. It's not an equation that you need to have memorized. It's an equation that you need to be able to come up with and use as the situation needs it. So we plug in that the period of this new satellite is 26,155.8 seconds. And that's squared. And that equals 4 pi squared over 6.67 times 10 to the negative 11 times the mass of the Earth, 5.98 times 10 to the 24th times r cubed. And so you solve that for r. So again, you would plug in all those numbers, take the cube root, and we get that the radius of the second satellite is 1.905 times 10 to the 7th meters. Again, this is the other common thing that you have to do, is find the radius of the orbit for a certain speed, or find the radius of the orbit for a certain period. This next problem is the same type of thing. A communication satellite is put into a geosynchronous orbit. A geosynchronous orbit is defined as an orbit that takes exactly 1 day to complete. Exactly 24 hours. So satellites circling over the equator will always be above the same point on the Earth. And we're going to find the radius of a geosynchronous orbit. So the period is 1 day, which is 24 hours, but 24 times 3600, that would be 86,400 seconds. Again, rather than just jump into Kepler's third law, let me just come up with it again. So the net force is the gravitational force. So that's G times the mass of the Earth times the mass of the satellite divided by the radius of the orbit squared. The net force is the mass of the satellite times the acceleration, the speed squared divided by the radius. Putting those two things together, the mass of the satellite times the speed squared divided by the radius equals G times the mass of the Earth times the mass of the satellite divided by the radius squared. The mass of the satellite divides out. One of the r's divide out. The speed squared equals G times the mass of the Earth divided by the radius. Again, one of the reasons to show this is we keep getting the same equation. It's the same equation that we keep using over and over. Sometimes we stop at this equation. Sometimes we go an extra step to the period, which is what we're going to do here. So again, remember that the speed is 2 pi r over the period. And so the speed squared will be that whole quantity squared. So 2 pi r over the period, that whole quantity squared, equals G times the mass of the Earth divided by r. So again, squaring all those things out, we get that 4 pi squared r squared over the period squared equals G times the mass of the Earth divided by r. Or again, rearranging it into Kepler's third law, the period squared is equal to 4 pi squared over G times the mass of the orbited object, which is the mass of the Earth, times the radius cubed. So again, in the end, this is the relationship we use to relate the period to the radius. So the period was 86,400 seconds squared, and that equals 4 pi squared over 6.67 times 10 to the negative 11 times the mass of the Earth, 5.98 times 10 to the 24th kilograms times r cubed. And so those are all numbers, so we can solve for r. And we get that the radius of the geosynchronous orbit is 4.225 times 10 to the 7th meters. Again, you should try plugging all those numbers in to make sure that that is what you get. But as you go through and look at that, you're using that same equation, and in the end, you are plugging in the numbers. And so the last thing, if we're asked what is the speed of the geosynchronous satellite, we could either use that the speed equals 2 pi r over the period. So that would be 2 times pi times the radius that we just found, 4.225 times 10 to the 7th meters, divided by the period, 86,400 seconds. And so if we do that, we have 2 pi times 4.225 times 10 to the 7th divided by 86,400. That gives a speed of 3,072.507 meters per second. The other way that we could have found this would have been that the speed was the square root of g times the mass of the Earth divided by r. Again, we had that as our other equation. We had that the speed squared equaled gm over r. So the speed will be the square root of gm over r. So this would be the square root of 6.67 times 10 to the negative 11th times the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, divided by the radius that we just found, which was 4.225 times 10 to the 7th meters. So we plug those in, 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by 4.225 times 10 to the 7th. That's 9,440,000, but we need to take the square root of that number. And again, that gives us 3,072.558 meters per second. Again, they're not exactly identical, and that's because the radius is slightly rounded, and the mass of the Earth is slightly rounded as well. Again, these are basic orbital motion problems. These are the most common things that you need to do. Usually it's going to be finding the speed given the radius. Sometimes it's going to be find the speed given the period. Sometimes it'll be find the radius of the orbit given the period. Again, there's quite a few different things. They all come back to applications of Kepler's third law. It's not a law that you need to remember, but you should be able to use Newton's law of gravitation to come up with it.